So let's go ahead and give it a there we go. All right, awesome. So here we are in week 7, and we're going to be talking about the laws of motion. So physics is all about scientists studying how things move and the way that things interact with each other and interact with the world. And in order to explain sort of the very basics of what are the rules for how things either start moving or stop moving, we're going to be looking at those rules today. So there's a set of 3 of them. We're going to cover the first 2 today, and then cover the third one and do kind of a review of all 3 for our Thursday class later on this week. All right, let's see. Let's get into it. So these laws of motion, you'll also sometimes hear them referred to as Newton's laws or Newton's laws of motion or Newtonian motion. It's named after this cartoon guy right here, who was in the mid 1600s, I believe, a real mathematician named Isaac Newton. Now, Isaac Newton is considered by many scientists to be possibly one of the smartest people that ever lived. He came up with an entirely new type of math called calculus. He's responsible most famously, or one of the things that he's most famous for describing is how gravity works. So he was kind of the first guy to figure out the reason why when an apple falls from the sky or from a tree, it goes down and lands on the ground. It doesn't just float away. But he's also responsible for coming up with these laws of motion. It's a series of 3 essentially rules of the universe. So that's why they're not called like the rules of motion or the theories of motion. They're called the laws of motion. Everything that we have found so far in the universe has to obey these 3 laws. So sometimes they have really short names. So they're usually referred to as law number 1, law 2, and law 3. So we have the law of inertia. We have the force equation, F equals ma, and our action-reaction law. Now, obviously, that probably doesn't mean a whole lot to you right now. But hopefully, by the end of today, you should know a little bit more about these first 2 right here. So we can also describe the laws, not just with short little names, but also in words. So the first law says that an object at rest will stay at rest, and an object in motion will stay in motion at constant velocity unless acted upon by an unbalanced force. The second law says force equals mass times acceleration. And the third law says for every action, there is an equal and opposite reaction. Some of this stuff you may have heard of a little bit before. Some of it may sound like I just said a whole bunch of made-up words. So if none of that made sense to you so far, don't worry. This is what we're going to talk about today. So for today, we're going to focus on these first 2 right here and really get into what do they mean, how can we describe them better, how can we put them into ways that make sense to you. So Newton's first law, the first law of motion, also sometimes called the law of inertia. There are a couple different ways that you can phrase it. One of them is the velocity of an object will remain constant unless a net force acts on it. You can also say, like I think I just had described in the earlier slide, an object at rest will stay at rest, and an object in motion will stay in motion at constant velocity unless acted upon by an unbalanced force. So by rest, you're going to see this come up a lot when we talk about the laws, especially this first one. Rest does not mean that something is like lying down or sleeping. It just means that it is staying still. So like my computer that you guys are looking at me through right now, right? My computer, when I put it down on the table and stop touching it, my computer, we would say it's at rest. It's not moving. There's nothing that's shaking it around or moving it or anything like that. So in physics, that's what we mean when we say at rest. We mean that it is sitting still, not moving. An object in motion will stay in motion at constant velocity. That's actually fun, but outside fun. So what does all this other stuff in here mean? What do we mean by will stay at rest, will stay in motion at constant velocity, unbalanced force? Essentially, it's a fancy way of saying an object is going to keep doing what it was doing the same way, the same speed, unless some sort of force, some sort of outside force comes and acts on it. So the first part, an object at rest will stay at rest, means that if the object is sitting still, like my computer right here, if I don't touch it and nobody else touch it, it's just going to sit on this table, right? If I leave the room and go out and leave the school and go home and come back the next day, if nobody's come and messed with it or touched it, or if there wasn't like a storm or an earthquake that blew it over, it's going to be sitting in the exact same spot that it was before. So it's basically saying things that are sitting still can't just randomly move on their own. Something has to come along and move it. Similarly, if something is moving at a constant velocity, it will keep moving. So the first law says that if something is moving, you have to put some sort of force on it in order to get it to stop, right? If you're in your car, you have to put on the brakes in order to get the car to slow down, right? Or if you're stopped at a stop sign, you have to hit the gas in order to get the car to speed up. So the whole idea of the first law is that it takes force to change the motion of an object. And force is like an outside influence that comes and is exerted on an object. So usually some sort of push or pull that is acting on an object. That is what a force is. And so the first law says that an object is going to keep doing what it was doing until something comes along and pushes or pulls it. So it takes force to get my computer to go from sitting still to moving, right? I have to pick it up and shake it around. It takes force in order to turn a car from going straight to turn over to the right, right? It takes force to change that direction. So when we say it will remain at rest or it will remain in motion, that's what we mean. It's going to keep doing what it was doing until some sort of outside force comes along and changes it. You may have noticed in that description, so we talked about sort of the first parts, an object at rest will stay at rest. If it's not moving, it's not going to start moving. An object in motion will stay in motion at constant velocity, meaning if something's moving, it's not going to speed up or slow down unless acted upon by an unbalanced force. So something that's sitting still or something that's moving is not going to speed up or slow down unless some sort of unbalanced force comes along and pushes it or pulls it and causes it to change speed or change direction. But so we've talked about this first part up here, and we've talked about this second part up here. But what does this unbalanced force mean? How is a push or a pull not balanced? Well, what we mean by that is that in order for forces to be balanced, it means that they have to be equally in opposite directions. So for example, if I take my computer or I take, I don't know, say a physics book or a big textbook and put it on a table, there's actually, it might look like the computer or the book is sitting still and there's no forces that are acting on it, but there's actually two. There's the force of gravity. So everything that is on Earth is affected by gravity. Gravity is what pulls us down to the ground and keeps our feet on the ground on Earth. So if you're out in space and you're way in deep space, then you don't have to worry about gravity. But as long as you're here on Earth, gravity is always going to be a force that is pulling you down. Now, the reason why the book doesn't just fall straight onto the ground, onto the floor, is because there's this table that's exerting a force back up on the book. So gravity is pulling the book down, but the table is holding the book up. They're both putting the same amount of force on the book. And so in this case, this book or my computer, the forces on it are balanced. There's an equal force going down versus going up. If the forces are balanced, then the movement is not going to change. This book was sitting still on the table. It's going to keep sitting still on the table until somebody puts an unbalanced force on it, meaning maybe they push it to one side or the other. Or maybe somebody comes along and adds to the upward force and picks up the book. So that is an unbalanced force. When you have more force in one direction than another, and it causes something to start moving or speed up or slow down. So if the forces on an object are equal and opposite, they're going opposite ways, but they're the same amount, then they are balanced forces. If they're not equal and opposite, that is what causes the motion of the object to change. So when you have more force in one direction versus other directions, that is when you change the motion. You get something to start moving if it was at rest, or you get something to slow down or speed up if it was already moving. All right, so if you're traveling along the highway at 60 miles an hour, right, the force of the wheels on the ground pushing you forward is the same as the force of the wind and the air and the friction on the ground pulling you backwards. So you're nice and balanced, and so you're traveling at the exact same speed. If you hit the gas, you'll add to that forward force and you'll start to speed up. If you hit the brake, you'll add to the backwards force and you'll start to slow down. So when the forces are balanced, everything stays the same. When a force is unbalanced, that is when we get motion. That's when we cause something to start moving, or when we get something to either speed up or slow down. So that is the basic idea behind this first law of motion. If something is staying still or something's moving, it's going to stay that way until some sort of unbalanced force comes along and changes it. All right, so we'll talk some more about different types of forces and the first law of motion. But does anybody have any questions so far? Anything about this first law or this idea of forces that isn't very clear or that you're still a little bit confused on? All right, sounds like everybody is feeling okay with this so far. So first law basically says that we need some sort of force in order to change the movement of something. The first law, it has another name as well. It's also sometimes called the law of inertia. So it's related to this idea of things staying still or things staying in motion. But inertia is the tendency of objects to resist changes in their motion, right? I can't just take my little finger and poke my laptop and cause it to move backwards a foot, right? Things resist changing their motion. And the amount that they resist depends on one single quantity, and that is the mass of an object. The more mass that an object has, the more inertia that it has. So basically, the heavier that something is, the harder it is to change its motion. So it's really easy for me to move my little computer mouse across the table, up and down with one finger. It's a little bit harder for me to do that with my laptop with just the one finger. My laptop has a lot more mass than my little computer mouse. So my laptop has more inertia. It's harder for me to change its motion. It's harder for me to speed it up. If it was already moving, it'd be harder to slow it down. And it's harder to change its directions. So again, something that instinctively kind of makes sense. Heavier things, it's harder to get them to move. That's basically what the law of inertia says. So again, the more mass that an object has, the more inertia that is present. Something that's really heavy, it's going to be hard to get it to start moving. So for a simple example here, think of these two buckets on strings. We've got one bucket that is totally empty and one bucket that is filled with sand. Now, I don't know if you guys have ever worked with sand before or had to carry sand around in big buckets. Sand is surprisingly heavy. It's a pretty dense material. So getting a bucket full of sand is going to make that a very heavy bucket. So that means that our filled bucket has more mass and therefore more inertia than our empty bucket, right? It's easy for me to give this guy a little push and to get him swinging back and forth. It's harder for me to push and get this guy moving. Similarly, if I give both of these guys two big pushes on this little rope swing right here, and they're swinging back and forth really big, it's pretty easy for me to catch this empty one and cause it to stop really fast. But this full heavy one, that's going to hurt if you let it hit you, right? This guy has a lot of inertia, so it's going to take a lot of force in order to get it to stop or slow down. Changing the motion of an object with a smaller mass is a lot easier than changing the motion of an object with a large mass. All right, so again, instinctively, this is something that kind of just makes sense, but in science, with everything, we have to give it its own special term and meaning, and we call it inertia. Same idea with this bowling ball and this tennis ball. If there's a bowling ball and a tennis ball, and they're both rolling towards you at 10 miles an hour, it's pretty easy to just stick your foot out and get the tennis ball to stop, right? Tennis ball is pretty light, doesn't have very much inertia, so you can stop it pretty easily. Bowling ball, you're going to have to put your whole body behind that one, because if you just stick your foot out, it's probably going to crush it and keep rolling on by. Bowling ball is a lot heavier. It has a lot more mass, and therefore more inertia. The bowling ball is going to take a lot more force in order to get it to slow down once it is moving. Same idea with if you had just some random guy running at you. versus if you had, I don't know, say a fully grown male bull elephant running at you. Man probably weighs, I don't know, 180, 190 pounds. Elephant maybe weighs 1,900 pounds. It's easier to push this guy to the side or push this guy down than it would be to change the motion of a running elephant. Elephants have a lot more mass, so therefore it is harder to get them to move or change direction or change their motion. That is all because of this idea of inertia. The more mass you have, the harder it is to get you to start moving. If you're already moving, the harder it is to get you to speed up or slow down or stop moving. And if you're moving, the harder it is to get you to change direction and move in a different way. And all of that is due to inertia. So it still takes force in order to get you to change motion, just like the first law says. But inertia says the amount of force needed is going to depend on your mass, how big you are. So essentially, if an object has a large amount of inertia, if it's really heavy, it has a large inertia, and that means that if it's moving, it'll be hard to slow it down or speed it up. It's why it's easier if you're ever at like the stoplight with a big like 18-wheeler or semi-truck next to you, and this light turns green, and you just kind of put on the acceleration, slowly accelerate, but you see that giant truck, it turns green, and then it's like, here we go. And that's because that truck is huge. It weighs tons and tons and tons. And so it's going to be really hard for it to start moving again once it's stopped. Same idea, it's hard to make it start moving if it's at rest, kind of like I was just saying. And then also it's hard to make it change direction. So the first law says that something moving in one direction will keep moving that way until a force acts on it. The more mass that something has, the harder it is to make it change direction. The more force that you need to get it to go one direction or the other. So another really good example of the first law and this law of inertia is that obviously, here on Earth, if you throw a ball or you throw like a rock or something, it's going to make kind of like an arc, but then it'll always come back down to the ground, right? So gravity is always pulling that stuff down, and it causes it to impact with the ground and stop its motion. But what if you're in space? What if there is no gravity around you to pull on these objects? Well, in space, if you throw a rock out of your hand, that rock isn't going to fall because there's no gravity. And so it'll continue to move in a straight line at a constant speed until it encounters some gravity from some other planet. So this is a great example of that idea of an object in motion will stay in motion until acted upon by a force. This rock, if you throw it when you're out in space, say it leaves your hand at, I don't know, 30, you gave it a good heave and it's heading 30 miles an hour. That rock is going to keep going at 30 miles an hour in that direction forever until something else comes along. So if it doesn't pass by any other planets or stars or anything, it'll keep going 30 miles an hour in that direction forever and ever and ever and ever and ever and ever. So this first law says that in order for this rock to slow down or to change direction, some sort of force has to come along and act on it. Some sort of force of gravity or something else has to be there in order to get the rock to slow down or change direction. If nothing comes and acts on it, it'll keep going in a straight line at that constant speed. Another great example of inertia right here. Both the car and the man are traveling at 80 kilometers an hour, about 45 miles an hour. The car suddenly hits this wall right here. The man, who is dumb and did not wear his seatbelt, is flung out of the car and over the wall. What's the reason for this? Why does the car stop, but the man doesn't? Well, the car stopped because something changed its motion. This brick wall right here put a big force on the car and caused the car to stop moving. The man, since he doesn't have a seatbelt on, and let's say that he flies right over the windshield, the man initially doesn't have anything that will stop his motion. So even though the car went from 80 kilometers an hour to 0 real quick, the man keeps going at 80 kilometers an hour, straight over the wall right here. So this is why seatbelt laws are so important. And this is why in car crashes, people can be flung out of their car because some force like a wall or a tree or another car acts on the car and causes it to stop. But if you're not wearing a seatbelt, nothing acts on you. So you're going to keep going forward, usually straight into the steering wheel or straight into the glass, or in a convertible, maybe even straight out of the car. You want to keep going at 80 kilometers an hour, even though the car has stopped. So a seatbelt is what applies that force on you. If this guy had his seatbelt on, he would start going forward when the car hit the wall, but then the seatbelt would act as a force against the man and would keep him inside the car. So here is a classic inertia at work. Nothing happened to change the motion of the man, and so the first law says that he's going to keep traveling forward at 80 kilometers an hour until something does change his motion. In this case, that change will most likely be his face on the pavement, and will cause him to slow down and stop. That is a lot worse way to go versus having the seatbelt be the reason why your motion gets changed. Again, another simple example right here. If you're doing some yard work, you have a wheelbarrow and you put the rake right across the top and you're wheeling it along, but then your wheelbarrow hits a rock. Ooh! So the motion of your wheelbarrow stops. But the rake still has inertia. The rake is still going to move forward at, 5 miles an hour. Let's say you're walking, you're pushing it pretty good. So you stop because you're on the wheelbarrow and the wheelbarrow has a force causing it to stop, this rock down here. There wasn't any force on the rake, so the rake goes flying off the top of the wheelbarrow. Again, this is what the first law is all about. The motion of an object is not going to be changed unless there's some sort of force that acts on it. If you're sitting still, you're going to keep sitting still until something comes along and moves you. If you're moving, you're going to keep moving until some sort of force comes along and causes you to change the way you're moving.
So,
yeah, did you have a question?
no, normal.
All right, got it. So like this golf ball right here. The first law says that if there was no wind and no golf club or nobody came and touched the golf ball, then it would sit on this tee forever. Right? Unless something came along and happened to it, that golf ball can't move off the tee by itself. There has to be some sort of force, like a golf club coming and hitting it, or maybe the wind blowing it over, or you picking it up and putting it somewhere else. It needs that force in order to come off of the T. So I've talked a lot about when things are in motion, they stay that way forever until there's some sort of force that acts on them. And that might have made you think, well, that doesn't really seem like it works. If I roll a ball along the floor, eventually that ball is going to stop. If I throw a football through the air, even if nobody catches it, eventually that football is going to come to the ground and stop. And that's because I've hinted at it already. But when you're on Earth, there's almost always some sort of unbalanced force that is acting upon the objects. One of the big ones that I've already talked about is gravity. So while you're on Earth, gravity is always pulling you down to the ground. So that's why things that you throw up in the air eventually come and hit the ground. It's because gravity is an unbalanced force that pulls things down. There's another force that causes things to slow down or change their motion, and that force is called friction. So friction is what happens when two objects roll or slide across one another. You can feel friction in your hands if you rub them together really hard, because the friction is what causes heat when you rub your hands like this. That's why they get warm. So there's a force in between your hands when you rub them together, and that force is called friction. We're not going to go into the details of like exactly how friction works. Essentially, it's like things aren't perfectly smooth, so there'll always be little tiny bits and crags that catch on each other. But the idea is friction is that even if something is rolling or sliding along the floor, along a table, eventually it comes to a stop, right? If you roll a ball along the ground, that ball is not going to roll forever. Eventually, it's going to slow down and stop. If I take my computer mouse and I slide it across the table, it doesn't slide very far. Even if I put a good amount of force into it, it only slides for like a couple feet before it stops. The reason that it stops, it's not because the like air pushed against it or anything like that. It stops because of friction between the bottom of my mouse and the table that it's on. So there's more main types of friction. We're not really going to get into the details of exactly what they are today, but there's sliding friction. So like two things going across each other. There's rolling friction, like balls or wheels rolling across the ground. There's fluid friction, so if you try to move really quick through water or through air, you feel air resistance. And there's static friction, which means that you have to put in a little bit of extra force in order to get things to start moving. But the whole idea is just that friction, two surfaces rubbing against each other, is usually an unbalanced force that'll cause things to slow down. So it's like if you're on a bike, when you're stopped at rest, there's no force that's acting on it, right? The force between the ground and gravity is balanced, and you're just standing there on your bike, so nothing's moving. So then you start pedaling, you're adding force to go forward. So now you're adding that force that you need that's going to change your motion and cause you to go forward. But after you pedal for a couple seconds, you start to feel tired out, so you stop pedaling. And even on completely flat ground, right? Eventually, you'll come to a stop and have to put your foot down so that you don't fall over. The reason why you come to a stop is there's this friction force between your wheels and the ground. And this friction causes your bike to slow down and eventually come to a stop. Same thing with if you're driving in the car and you're driving along the road and you lift off the gas pedal, right? If you're going at 60 miles an hour and you let go of the gas pedal, are you just going to keep going at 60 miles an hour? No. There is friction between not just the air and your car. So as your car is going through the air, there's a little bit of friction there. But there's also friction between the wheels on your car and the asphalt, the ground that you're going over. So eventually your car, you start off at 60 miles an hour, and even though you're not doing anything to change the motion, your car slows down and slows down and slows down and slows down until eventually it stops. I guess, I mean, like in most cars, you don't actually stop, but you slow down until it starts doing that like 1 to 2 mile an hour kind of creep forward. But friction is what causes your car to slow down. So on Earth, things don't travel forever and ever and ever because of friction. Friction is almost always an unbalanced force on any moving object that resists its motion and causes it to slow down. It's essentially a force in the opposite direction of how the object is moving. So friction is why, even though the first law says that things in motion will stay in motion unless there's an unbalanced force, on Earth, friction is usually that unbalanced force that causes things to go from moving at a certain speed to moving slower and slower and slower and slower. It's all because of friction, this rubbing or this rolling of two surfaces on one another. So again, if you think back to that example with the rock and the astronaut, or something like a rocket ship, right? Once we get out of Earth's orbit and once we're away from the planets or in space, when a rocket ship has a certain speed in a certain direction, if it doesn't fire any of its other boosters or it doesn't hit any planets or any suns or anything like that, that rocket would keep going in that same direction and at the same speed forever. In space, there is no friction and there is no gravity that are acting against our movement. So in space, things are able to keep going at the same speed and same direction forever, or until something comes along and changes the motion. Let's see. Momentum is another type of quantity of movement, but we're not really going to worry about momentum in this class. It's kind of similar to inertia, but a little bit different. But we're just going to kind of skip over it. I thought I had taken these slides out, but I think that was in a later version. This is an earlier version. Okay, so before we move too far away from it, does anybody have any more questions about the first law of motion? Anything about inertia or friction or anything like that that still is a little bit confusing or you still have questions on? All right, sounds like we're all good with the first law so far. So again, first law of motion says things that are still will stay still, and things that are in motion will stay in motion unless some sort of unbalanced force acts on them. Maybe gravity pulls them to the ground, or friction causes them to slow down. But if there is no unbalanced force, then they will stay still or they will stay in motion that same speed forever, essentially. We have to have force of some kind in order to get the movement of an object to change. It can't change for no reason all on its own. There has to be some type of force, some type of push or pull that changes the motion of an object. All right. So up next, we have our second law of motion. And the second law is actually a simple equation, kind of similar to our density equation, that describes a relationship between force, mass, and acceleration. And the second law very simply states that force equals mass times acceleration. F equals ma. So obviously F is for force, the amount of push or pull. M stands for mass, the weight of the object. And A stands for acceleration, how fast an object is speeding up or slowing down. So acceleration is how quickly an object is changing speed and direction. So F equals m times a. Force is equal to mass times acceleration. The higher the mass or the more acceleration that you have, the higher force that was applied. Force equals mass times acceleration. This is the basic principle of our second law of motion. F equals ma. So force and mass and acceleration are all what is called directly relational or directly proportional, meaning that if one goes up, one of the other ones has to go up as well. So, for example, if you were pushing like a cart or something around and it had like a little box on it, you put in a certain amount of force, and based on the mass that you have, you're going to get a certain amount of acceleration. So if you multiply the mass by how quickly you cause the speed of the cart to go up, you can figure out the amount of force. If you put in more force to the cart that has the same mass, you're going to get more acceleration, right? F equals ma says that if the F goes up and the m stays the same, we still have the same size cart with the same size box, the A is also going to have to go up. Again, something that is kind of simple in terms of thinking about it. If you push something harder, it'll move faster. But Isaac Newton and physicists have figured out a way to put it into mathematical terms. So if you want to make something move faster and you have the same object, you can put more force in and it'll speed up faster. Similarly, if something is heavier, it'll take more force to move it the same way versus something that is lighter. So in order to get this cart down here to accelerate, that just has this one little, I don't even know what this is, like statue. Let's say it's a little statue. You got one little statue on this cart. You pull it with a certain amount of force, and it's going to accelerate a certain amount. If you have more mass and you still want it to accelerate that amount, you still want to get it moving at the same speed and the same acceleration. If the mass is more, then you're going to have to pull it harder. All right, F equals ma says that if you want the A to stay the same and the m, the mass, goes up, your force is going to have to go up as well. So again, simple idea put into physics terms. The heavier something is, the harder it's going to be to pull the same way as a lighter thing. The more mass that an object has, the more force you're going to need to accelerate it versus accelerating something that is lighter. So if the mass is the same, if something stays the same, more force is going to give us more acceleration. If the mass of something goes up, then we're going to need more force in order to get that same amount of acceleration. F equals ma. The amount of force that is put into it is equal to how heavy the object is times how quickly it speeds up or slows down. So you can use this equation to figure out either based on the force of an object on an object, how quickly is it going to accelerate, or based on the acceleration of an object, how much force did you use on it? So in like a soccer example down here, you can measure how heavy the soccer ball is. You can get its mass. And then when somebody kicks the soccer ball, if you have one of those little like radar guns, like police use to look for people who are speeding, you can track the ball with the radar gun and figure out its acceleration, figure out how fast it came off this guy's foot. And so if you know the mass and you know the acceleration, you can multiply those together and figure out how much force did that soccer player put onto the ball. How much force did they kick the ball with that led to the ball, which weighs a certain mass, accelerate off their foot at a certain speed? So that is what we can use the second law to figure out. There's always going to be this very direct relationship between force, mass, and acceleration. So F equals m times a. Force equals mass times acceleration. If you can measure the mass of the object and you can measure how quickly it speeds up or slows down, then you can do a simple little equation to figure out how much force was exerted on an object. All right, any questions about our second law of motion here?
How would you type it up on the calculator? So it's just weight times speed equals force?
Yeah. Let's go back. So yeah, mass is, if you put it on a scale, how much would it weigh? And then acceleration is a little bit different than speed. It's essentially how quickly is something speeding up. So for example, if something goes from like 10 miles an hour to 20 miles an hour in the course of 1 second, then we could say that it accelerated 10 miles an hour in that second, right? If it went from 10 to 20 and it took a second to do that, then its acceleration would be 10 miles an hour in 1 second.
Okay.
So like a lot of times when people talk about sports cars, they talk about like, oh, it can go from 0 to 60 in 4.2 seconds or 2.9 seconds. And so let's say if a car goes from 0 to 60 miles an hour in 3 seconds, then its acceleration would be every second it's going 20 miles an hour faster, right? On average, on that first second, it got from 0 to 20, and then the second one, it got from 20 to 40, and then the third one, it got from 40 to 60. So in that case, the acceleration of that sports car that went 0 to 60 in 3 seconds would be 20 miles an hour a second. So acceleration is related to speed, but it's more accurately saying how quickly is it speeding up or slowing down. All right, good question. Anybody else have any questions about our force, mass, acceleration, second law, F equals ma? right. So that is actually where we will take a break for today, just because the third law can be a little bit tricky. And so I want to make sure we have plenty of time to work through it and talk about it on Thursday. So on Thursday, we'll come back and talk about the third law of motion and kind of review all the laws of motion together and see how they all work together to help explain some of the basic rules for how things in the universe move. All right, so the daily assignments for this week, since this is all pretty new stuff, are all pretty simple. I wanted to make sure that people weren't getting overwhelmed here as we get close to the end of the term. And so I think today's assignment, I just want you to ask you guys kind of in your own words, how would you describe the first law of motion? And then tomorrow's assignment, I want to see if you can remember that equation that describes the second law of motion. So 2 simple questions for today's and tomorrow's assignment. And then again, on Thursday, we'll talk about the third law of motion and kind of review all of the laws of motion together. All right, does anybody have any final questions about that first law of motion with the inertia and the unbalanced forces, or the second law of motion with the force equation and the F equals m times a?
No question.